Welcome to Physics 1, first video lecture. This is the introduction to motion. I'll also add in constant velocity and acceleration. So this video will be just a little bit longer than normal depending on the different examples that will be used in future lessons. But this one has 3 concepts in it where usually I cover one concept at a time. But welcome. All right, so as we're diving into motion, we're going to try to understand motion in a narrative form, a mathematical form, and graphical representations. And so all the videos that will come after this, all discussing motion, will be covering one or multiple of those 3 descriptions of motion. All right, but today we're going to really look at all 3 of those in just a very simple listic, but actually we're going to leave the graphical out of it until a later lesson. All right, so acceleration, just want to make sure we have some key things moving forward. As we use this slide, I'll kind of highlight some important information as we move forward. And so for this particular lesson, I'll make sure you have some very important information taken away from it. That there, the very first bullet is the quantities that we'll be looking at are positions, displacement, distance, velocity, speed. The big thing is acceleration is based on a frame of reference. And we'll talk about that in a moment. All right, displacement, velocity, and acceleration are all vector quantities, so we'll need to define what vector and scalar quantities are. So let's just do that now. So scalar and vector quantities have one thing in common, and then they have basically one thing that's different. So I used a Venn diagram here to describe and look at those similarities and differences. But the similarity is that they have a number associated with them, like 25 meters, 5 seconds, 35 kilometers per hour. Okay, these are all scalar quantities. The difference is that vectors, to make it a vector, I need to add a direction. So 35 meters per second, south, north, east, west. They went 15 meters east. All right, and I put this little diagram over here in the vector side that in the looking at the coordinate system, or north and south, east and west. This is what we would typically do in physics. That if I say it's east, it would be positive, west would be negative, or left, right, up, down. That's just typical based off of the coordinate system that you learned in Algebra 1 or maybe sooner. So just kind of keep that straight. That's what we're going to use typically, but ultimately I get to decide as the person who's deciding the frame of reference. In a second, frame of reference is simply an idea that the individual who's working the problem or seeing the phenomenon occur, or this motion occur, is the person that's looking at it. And so depending on where you are, it kind of affects what you see. So we'll kind of look at this here for a second. So I have scenarios here. Ashley's moving to the right at 5 meters per second. Bob's moving at 2 meters per second. Caitlin's moving the opposite direction at 2 meters. And Dan is just standing still. All right, he's no exercise for him whatsoever. He doesn't want to go. He doesn't want to leave school. Maybe that's what it is. But here's just kind of some questions here on this side. It says, how does Ashley appear moving to Bob? Well, if I'm sitting in Bob's seat, all right, and I look at Ashley, what would I see? Well, I'm already moving at 2 meters per second, so the only thing I see different from what I'm doing is that she's increasing, speeding up around me, or however you want to think of it, at 3 meters per second. So she's not driving much faster than I am. But if I was in Caitlin's seat looking at Bob, Bob would be flying away from me in the opposite direction at 4 meters per second because I'm moving in the negative direction and he's moving in the positive direction. So I would add those 2 directions together instead of subtract them. And then if you have Dan would actually be setting at 0 and he would just be seeing Bob move nice and slowly down the road at 2 meters per second. So it's just kind of an idea of frame of reference that you have this, you as the person working the problem or standing still gets to decide what's going on. Most of your frame of references that you'll be used, unless otherwise stated, will always be as if you're standing outside of it looking at it like Dan is. But there will be a couple of cases in which they'll put you in Bob's seat or Ashley's seat and ask you to describe what's going on. But most of the time you'll be in Dan's viewpoint. All right. So let's look at the very first variable that we'll need to describe motion, and that will be time. So time. I'm going to use the symbol for my equations and calculating time for lowercase t. There are no variations because time is time, all right? And so there's your definition. There's the SI units that we'll be using, and time will always be a scalar quantity, all right? Now, moving forward, here's some subscripts that will be used with these variables. So time, we'll get to position in a second, so on and so forth. As we move forward in physics, I'll be using these subscripts throughout. Now, this subscript right here, the not symbol is what I call it, the 0, is for initial, and this is the predominantly the one that we'll be using the most when we calculate different types. And so you'll see kind of down here at the bottom that I have final minus initial or final minus initial, but we'll typically use the F minus the not symbol, all right, for initial. And sometimes if we have this not symbol, we'll drop the F, and so for the final. So don't be shocked by that. So if you use this, typically we won't use the F, but if we use the I, we definitely will use the final every single time. All right. And now the next thing you also need to know is actually, while we're down here, is this triangle. This is called delta. It's the Greek letter for delta, and delta will always be known for final minus initial. No matter what the variable is, no matter if it's x, y, z, 34, it doesn't matter what this symbol here is, delta will always mean final, whatever that symbol is, minus the initial, whatever that symbol is. And so I just made up a character here. I don't even know what that is. Just kind of proving that point. All right. So let's look at position. Position is unique. Position tells you where something is relative to the frame of reference. All right. And I'm going to use the lowercase x here. Sometimes if it's in the y direction, I'll use the y. But x is the uniformal variable when we talk about position. Its SI units, its base unit will be in meters, but we'll look at kilometers, picometers, centimeters, all those things. And then you see the variations that are down there, and you'll see a commonality as we move forward. Displacement down here is a new, not new, it's kind of the old way of doing things. But I did want to put this in here in case you got any old type of problems and wondering what in the world was the D for. And that's just simply position. All right. And displacement, as we're talking about it, is delta x. So it's change in position, final position minus the initial position in a straight line. So distance and displacement are actually two separate things. Distance and displacement are two separate things. All right. Distance is how far an object moves, so it's scalar. Displacement, however, is the final minus initial, and it has direction, so it's a scalar quantity. All right, and we'll work with displacement in our problems as we move forward once we get to more complicated matters, but they always will sound like distance. All right, so it's kind of the tricky thing when we talk about position, is that displacement is really what we're calculating. However, sometimes it kind of translates into position, so just keep that straightforward. Okay, so let's kind of do some vector adding. It's pretty straightforward and simple. You add always head to tail, or tail to head, whichever way you want to say it. But right here you can see I don't have the little dots connected together. I have head and tail connected together, and so you just simply add. All right, so this is 10 meters plus 5 meters, but it's in the opposite direction, so it's negative 5 meters. So it would be 10 minus 5, giving me 5 meters. Okay, so if I were to look in the two-dimensional standing, I'm going to use the Pythagorean theorem, as you can see right here. All right, so my displacement actually for this particular one sits right there. Okay, and so 10 squared plus 7 squared is going to give you 12.2 meters for that. Okay. All right, so the next symbol that we're going to talk about, or our next type of motion, is velocity. All right, and velocity takes it to the next level. I actually use position, where I'm at, what's changing about it, and the time it takes to do that change. All right, and we call this velocity. All right, so this would be displacement divided by time, right, which is our average velocity. So final position minus initial position divided by time gives it to me, and then again, there's that old way of writing it, or what you might have seen it in physical science or something like that. Okay, so speed of an object and its direction is called, or the rate of displacement is another way of saying its definition, is velocity. Okay, so speed is the same thing except it doesn't have direction. Okay, so speed is just meters per second, no direction. Velocity is meters per second, south, north, left, right, positive, up, down. All right, you get the gist. All right, and then you see all the variations that you see. Again, we're going to primarily stick with these three. These two are a little older ways of writing it, but I did want you to see them as well. All right, so let's look at a practice problem, calculating velocity and displacement and kind of seeing how this all works. All right, so I have a beetle. It's been placed in a square box. Each box edge is 5 meters long, and if the beetle starts at the top left corner, it travels directly right until it hits the next corner and then turns straight south until it reaches the bottom right corner. Question 1 asks, what is the distance the beetle traveled? All right, so let's kind of get a picture here, because the pictures always matter to us. Okay, the frame of reference. So here's my box. I have my little beetle. Let's get him in there. All right. No judgment on my little beetle. So my little beetle goes to the right, straight right until it hits that corner. And then he goes straight south to hit that corner. Okay. And the problem specifically says here that each side, it's a square box, so each side is 5 meters. So 5 plus 5 is what? 10 meters. So distance, calculating distance is really easy. Displacement, that's a different thing. Because displacement here, let's change it so I want to get you to see a different color here. Displacement changes it. The displacement of my little beetle is actually right there. All right, it's not following the same path that the actual beetle took. All right, so I'll just keep this in green. And so we just did that earlier, so that's just 5 squared plus 5 squared. All right, so my displacement for my beetle is 7.2 meters. Now, I want to take a time to pause here and really understand what just happened. All right, because this is an algebra-based physics class, I'm going to do the algebra in fast mode. All right, I'm going to fast forward through all my writing because you should be able to do that at a basic level, because everyone in here should have at least Algebra 2 or be taking Algebra 2 at this time. So you should already gone through basic algebra and you should have already mastered it. So I'm going to just kind of fast forward through those moments, but I'm going to write them just in case you need some extra support. Now, in class, I'll go over significant figures. I've already posted other teachers from the web that have already made videos of how to calculate significant figures. So I want to have you watch them. There's no reason for me to repeat what is already out there, but really pay attention to significant figures. But for this video, we're going to kind of ignore them just to get the basics. But from here on out, we will pay attention to significant figures and how to round them. All right, so what's our next variable? We have time, we had position, we have velocity, and the final type of motion is acceleration. It's not the final type of motion, that's a really bad word, sorry. This is the final one for this video, all right? So acceleration, I'm going to use a lowercase a. It is the change in speed, or what we call the rate of velocity. The word rate simply means change in, all right? So if you keep seeing that word rate show up, you know what it means. Change in whatever comes after velocity. All right, so acceleration is change in velocity. So I want to have that final minus initial that you see me have highlighted down here in the special notes section. Now, the unit here is actually meters per second squared, because I have meters, I have my position divided by my time again. So I have 2 times here, and I have meters per second, which we can translate to or simplify to meters per second squared. Okay, and so I do want to make a change or make a note here that acceleration happens in three types of forms, and that's speeding up, slowing down, and changing direction. We'll get into more of why acceleration is, when changing a direction changes your acceleration, or that you are accelerating later in the physics class, but I want to make sure you know it now that changing your direction causes acceleration. All right, and so basically, so I know how to slowing up and slowing down, what that looks like is basically if my signs are different, negative and positive. Okay, if my velocity is negative and my acceleration is positive, I'm slowing down, or vice versa. If they are the same, if I'm increasing velocity, increasing acceleration, I'm speeding up. If I'm decreasing velocity and my acceleration is negative, I'm slowing down. All right. So basically, what I mean by is signs disagree, they're opposite. Signs agree, they're the same. Speeding up, they agree. They slow down, they disagree. All right. And so I do need to make one more additive before we go on to a practice problem, because I'm afraid I might have misled you. In physics, the direction matter. They're represented by positive and negative. But the tricky thing is, in physics, the sign is only about direction, not value. Because I can find my velocity. If I find my velocity to be negative, that would mean I'd be going less than 0 movement. Well, I can't do that. That's impossible. But I can say it's opposite direction. And so keep that straight, that the signs in these problems are actually direction, not value. So you can't have less than 0 time. You can't have less than 0 movement, but you can have opposite. And so that's the real distinction between math and real-world physics. All right, so let's look at that problem. All right, so a relay runner is sprinting north at 3 meters per second. She reaches her goal and manages to turn around and run straight south at 4 meters per second in 2 seconds. What is her acceleration? So again, let's draw this out. We gotta always draw our problems. So I go north for 3 meters per second. Let's do scale just a little bit, so we'll make that a little shorter. And then let's change our color for our direction. Let's say it's red at 4 meters per second. All right, let's get our labels on there. So this is 3 meters per second. This is 4 meters per second. And the whole thing takes me a time, so all of this takes me a time of 2 seconds to occur. So she is really fast, or he is really fast. Or excuse me, she is really fast. So looking at this, I'm going to have acceleration, right, is my final position minus my initial position divided by time. All right, and so again, there's my answer for the acceleration for the first part. And then what is the direction? Well, I left it off, but we calculated it right there. But I left it off for this one, so it's going to be down, right? So she is running south, so my final answer is south. All right. So good luck.